Good evening, everyone. So, any more has to join the class, or we can start?
Good evening, sir. Good evening, sir.
Shall I start?
Hello, good evening, sir.
Yes, good evening.
Sir, that would be your call, sir. You can definitely start with the class.
Okay, I am starting now. So, is the screen visible?
Yes, sir.
Okay. So, today I am going to cover the basics of data acquisition and microcontroller. So, after this class, you will have a practical overview of the microcontroller applications in the practical world. So coming to the data acquisition, actually data acquisition means we have to acquire the data from the physical systems which are around our which are in our world. Maybe it may be robotic application, or it may be automation in an industry, or it may be an automobile. So the purpose of the most electronic system is to measure or control some physical quantity. So here, whatever physical quantity is there, it may be the rotational speed of a motor, or it may be simply sensing of some voltage, or sensing of temperature, pressure of certain system. So that through some sensors, we will gather the physical, we'll sense the physical quantity that need to be acquired and given to a relevant digital system like a controller or a processor, so that it can take certain action. So, even the control systems also, we need to interact with the environment. For that purpose, we need to sense the physical quantity. So these are the typical steps involved in data acquisition. First, the transducers measure some property of the environment. A transducer any kind of device which converts one form of energy to another form. For example, a motor. A motor can be called as transducer, which is converting electrical energy into mechanical energy. So, like these transducers, we need a transducer to measure certain property of the environment. So this transducer need not be an actuator, that can be like sensor also. So these sensors also interacts with the physical world and converts the physical quantity like mechanical energy or any other light energy into an electrical energy. So that can be acquired. So the output of the transducers in the next step is conditioned. So conditioned means it is like amplified or filtered so that the noise levels are reduced. Suppose we have a sensor which is producing a millivolt voltage signal in the range of millivolts. So now when we come to acquire the data of that signal, so our DAC may have acquisition range from 0 to 5 volt, but the sensor is giving a millivolt range. So that signal need to be amplified so that we can suitably read it and acquire through the DAC module, DAC ADC module. So now the condition signal needs to be digitized through using an analog to digital converter. So what is the analog signal here? Analog signal is a continuous time domain signal where for any given time there exists a signal quantity. And digital means that is a discrete signal, like at time t equal to 0 there is a value, at time t equal to 0.1 second there is a value, but in between there may not be any values. So that kind of signals are called digital signal. So our computer stores everything in kind of digital format. So whatever quantity we are sensing, that is converted to an electrical signal through a sensor, and that needs to be digitized through ADC module, and that needs to be amplified, filtered through relevant hardware, and then that needs to be fed to the computer for quantization. Quantization means that discrete signal has to be amplified suitably so that we can give the input to the microcontroller or microprocessor. So here we can see in this image that the left hand side shows the physical quantity being measured. It can be anything, like it may be a temperature data, pressure data, for example. And you can see that it is a continuous line. That means for any given time there exists a value for this physical quantity. So for storing this signal, we cannot store infinite number of time samples. So we will discretize the signal for a given time interval at a regular frequency. So here you can see that the vertical lines drawn, those are the sampling times. So at a different instance, the signal is read and given to a digital filter. So here, while we are doing sampling, we need to see that the actual information in the analog signal is not lost. For that, we need to follow this criteria where the sampling theorem, particularly Shannon's sampling theorem, states that we need to sample the signal at a rate at least twice the maximum frequency of the frequency component in order to retain all the frequency components in the signal. Suppose there is a 1 hertz frequency sine wave. So our sampling frequency should be at least 2 hertz so that the signal information is not lost. So this mathematically can expressed as Fs is greater than 2f max. Fs is the sampling frequency and f max is the maximum frequency component present in the signal being sampled. So this criteria is also called Nyquist criteria, or the frequency of the sampling is called Nyquist frequency. So here, when we don't do this sampling properly, the actual signal which we are using, which we are sensing, when we sample at a different frequency, means lesser frequency than the Nyquist frequency, then the information would be lost. So that then when we reconstruct the signal from the discretized signal, we will get entirely a different signal. So that new signal, which is different from the original, called the alias of the first one. So this kind of effect is called aliasing. So in order to eliminate this aliasing effect, we should follow this Nyquist sampling theorem, which we have seen that it states that the sampling frequency should be at least greater than twice the highest frequency present in the signal. So here we can see the effect of aliasing. So suppose these signals are sampled at different frequencies of the waveform cos 60t. So the first image shows that the sampling rate is 0.001 seconds, that is 1 millisecond, and the second one is at 0.01 second, and third one is at 0.05 second, and fourth one is at 0.1 second. You see that at each for each of these sample signals, when we reconstruct that signal, how the signal is being the reconstructed signal is being different from the original. So to depict that, say suppose we have a sine wave or cos wave, which is at whose time period is say 1 second. So from 0 to 0, it is 1 second. Suppose if we sample at say 0.5 seconds, so our sampling time period, so delta t is 0.5 second. Then the frequency becomes 1 by delta t, or in the sampling period is defined as t, then that is 1 by t, that is 1 by 0.5, that is 2 hertz. Okay, so now if you take the signal at every 0.5 seconds, so now the discretized signal will have 3 points, that is at t equal to 0 physical quantity, or I will write signal quantity s is 0, then t equal to 0.5 seconds, s is again 0, then t equal to 1, s is 0. Now the computer will only see the discretized signal values, and when it tries to understand that when you reconstruct with the help of these points, you can see that we have 3 points. Now when you draw this, when you draw a straight line connecting these points, then the reconstruct signal is entirely lost from the original. Suppose if we sample at 0.25 seconds, then we'll have 5 points, that is at t equals 0 it is 0, at t equal to 0.25 the amplitude is 1, then again at 0.5 it is 0, at 0.75 the amplitude is -1, then again at t equal to 1 it is 0. Now if you try to reconstruct with help of those additional sample points, at least we will get that signal which is closely representing the original one, but here also some of the information is lost. So like this you see that this cos 60t, the original signal is sampled at different sampling rates. Now when the sampling frequency or sampling time is 0.1 second, you see how the signal, the reconstructed signal is lost. So suppose this how is it obtained? If suppose this is the original signal, it is sampled 1 point here, and it sampled 1 point here, 1 point here, 1 point here. So like this, if it samples, now the reconstruct signal will be something like this, which is entirely different from the original signal. So here, while acquiring the data, we have to keep in mind that we have to at least have a sampling frequency that twice the maximum frequency component present in the signal, in order to avoid this aliasing effect. Otherwise, we will be losing the original information, then all our process which are using that signal can go wrong. So here this block diagram shows the analog to digital conversion module. So basically mostly it can be a hardware device which is following these steps. So in the first one, the sensor reads a physical quantity. So the read physical quantity, maybe that voltage may be very less, say suppose in terms of millivolt. Now so that is stored in the buffer amplifier of the ADC device. So what it is doing, it is storing that signal and amplifying into a suitable range, maybe which is 0 to 5 volt or 0 to 10 volt, depending on the DAC hardware capability. So after amplifying, now we got the signal into suitable range. Now that signal is passed through a low pass filter. What this low pass filter is doing, low pass filter is again a filter which passes only the lower frequency components. So here whatever the noise is present, so here you can see suppose the signal is having so much noise, which is this variation in the measured quantity with rapid variation. So this component present, this component is high frequency component, which is eliminated when we pass through the low pass filter. So this low pass filter, in general sense, it can be a software filter also, but in ADC it is a hardware filter. So now the signal is conditioned by removing the high frequency components. Now it is passed to sample and hold. So here it will sample the data at different time points. So for example, we want to read the signal at this point. Now it holds this value for a particular brief amount of time. So now the analog to digital converter will read this value, what is the quantity from the reference value. So now that quantity is converted into a binary format, which is a number, so which can be stored in the memory of the computer or a processor, which can be used for some other purposes like feeding the input to a control system, or simply storing the data and plotting, visualization, etc. So coming to the microprocessor, so let us see some brief concepts about microprocessor and controller. So first, let me introduce the microprocessor. So as this is just a brief orientation, I'm not going into too much details of these concepts, but this should give you a practical orientation to understand the terms and nomenclature associated with this. And as a GRAS user, you should have some understanding about these devices. So here a microprocessor is a single very large scale integration chip. So that contains many digital circuits that perform arithmetic, logic, communication, and control functions. So here, suppose logic unit where it performs a simple operation a plus b equal to c. So that may be a small hardware logic circuit. So like this, many circuits combined together forms a very large scale integration chip. So which will be used for solving any arithmetic calculation, or computing some logic, or communicating with other devices, or producing some control input, and by taking control input and producing some control output. So we have seen in our day-to-day life the microprocessor like computer. When we talk about computer, we used to see the processor generation like Intel i7, i5, like that, the frequency associated with that. So these are the microprocessors. So they are generally packed on a printed circuit board with other components such as interface and memory chips. The resulting assembly is referred to as microcontroller or a single board computer. So in robotics application, we generally use these single board computers. They are also commonly referred as SBCs. So they are what they are containing. They are containing the microprocessor along with the other peripheral components such as memory devices for storing and execution of the program, or storing some data. And so this is the architecture of the microcomputer, where the microprocessor unit is shown here. So there is a control unit, data registers. So the registers are the memory devices which will store certain data, and they are associated with certain address. So particular data can be accessed with the help of the register address, and instruction register, where the instructions are stored in the particular registers. So and the instruction decoder. So those what this instruction decoder will decode what the particular instruction is and what to execute, and this arithmetic logic unit performs the computation. So in order to function this microprocessor, we should have a RAM, ROM, and EEPROM kind of memory devices. So RAM is a volatile memory, and ROM is not a volatile memory. So RAM volatile memory means like this is a kind of temporary memory where we are suppose when we are solving a problem. So we used to do rough work, right? Like that. If we want to store something temporarily, we can use RAM, that is random access memory, and this one ROM is for read-only memory. So where we can store the data permanently, which is erasable, but you can store the data, and that data will not be lost even when the power is lost. So on the other hand, RAM stores the data, but when the device is powered off, the RAM memory will be lost. So for any temporary storage, while performing these arithmetic logic operations, we can use that program will make use of RAM. And for storing any data or program instructions, we will be using ROM. And this is EEPROM is also kind of ROM memory, which will be used for storing the data or some programs. So for interaction with the device, so we will be needing external input output devices such as analog to digital converter, digital to analog converter, or digital to digital converter. So these may be interfaced with switches, sensors, and actuator depending on the applications, and that may also have external mass memory like CD-ROM, which it can read the data from compact disk. And in order to interact with the system, we may also be having keyboard, printer, monitor, like that. So the same architecture like can be there for a PC or an SBC. So PC generally it is a large system associated with all peripheral components, and SBC generally it is a very small computer that is a microprocessor and packed with all the additional peripheral units in a single board. So these SVCs are very much useful for robotic application where you want to write very say intensive programs having several lines of code which is useful for any control application or any artificial intelligence application where it has to read a lot of data and analyze it, learn it, and execute, take decision based on the physical environment. So for programming these devices, there are different codes. There are different kinds of methods. So we'll see one by one. First, it is the machine code. The machine code, nothing but instructions that can be executed by the CPU by a binary code called machine code. That means suppose see at the end whatever we want to interact, the computer can only read the binary digits like this. So if you the machine code, suppose I am writing this some sample code like this. So depending on the processor type, particular binary code tells the processor to do some particular operation with the particular data. So if you write this kind of code, that is referred to as machine code. But for human beings, writing machine code would be very difficult. So generally, we will not follow this approach. So, but we need to convert whatever the code we are writing that into a machine code so that the computer can understand and execute it. So again, assembly logic, assembly language. So this is one level above the machine code, where microprocessor can be programmed using assembly language, which comprises mnemonic commands such as this add or move. So suppose if I write add a comma b, so it is saying that it is we are instructing the microprocessor to add a and b, that is perform a plus b operation. So like this, whatever machine, whatever these codes are there, keywords. So that one will again corresponds to a particular binary code depending on the processor. So whenever we are using, we are writing the program in an assembly language. So still we will be using this mnemonic commands. So that finally needs to be converted into again machine code. For that, we will need some other interpreter or assembler. What it does is all these commands are converted into again binary code so that the microprocessor can understand and execute the instructions. So now the most many of you may be very much familiar with these higher level languages such as basic or C. So here we can easily understand these higher level languages. So these again, whenever we are using these higher level languages, again these has to be converted into machine code. For that also we need a compiler. So whatever we are writing the commands, that that has to be specific to a particular processor or a controller. So now these are the advantages and disadvantages of the higher level languages. So here we can easily understand the higher level language. Say for example, I am writing say you can directly write the code like this: a equal to b plus c. So b equal to 12 and c equal to 10. So we can define these variables as integer a, b, c. So this, even if you don't know the particular syntax also, you can very easily understand. And this kind of language is called higher level language. So the advantage is ease of learning and using is very much easy. And you can also debug the programs. Suppose instead of that, if I write 110000111112, sorry, 11011. So like this, if we write directly the machine code, it debugging is also difficult. Or even the assembly language we can use for microcontrollers. That though it is a efficient way of programming it, but still it poses difficulty to learn and use, and also for debugging. So the disadvantages include that it may be very less efficient, and when so as here we are not directly instructing the microcontroller or processor how the code should be executed. It all depends on the compiler, how it is compiling and turning it into a machine code. So that still it is a man-made compiler, so it may not have so much intelligence to make the efficient program. So whatever we are writing in higher language, that through compiler it is converted to machine code. So for that, it may add the inefficient commands. So coming to the microcontroller, so we have seen that microprocessors on them itself, when you go for the microcontroller architecture. So here we can see that these microprocessors don't have onboard memory devices. So we need to add onboard memory devices and external input output devices like that. But when we add all of them on a single chip, all the memory devices and input output capabilities and a single chip, then it can be referred to as a microcontroller. So there are a few, for example, there are popular microcontrollers like big microcontroller or Intel 805, 8096 or 8051 microcontroller like that. So these microcontrollers are very much required for the developments in robotics or any industry applications. So there are some factors which have driven the development of these microcontrollers, such as low cost. Like the cost of a microcontroller is just a few hundred rupees compared to a microprocessor. So the microprocessors are in terms of few thousands to few lakh rupees, and the versatility is good in case of microcontroller. So they can be used for some dedicated application where they can execute the code very efficiently with a proper timing. So ease of programming and small size. So these are all the factors that have driven the development of microcontrollers for different applications. So coming to the applications of these microcontrollers, there are several applications in our real world. So coming to some few examples, that entertainment equipments or telecommunication equipment or mechatronic systems such as washing machine, TV, or a microwave oven like that, or be it automobiles or airplane or toys. these are all contains microcontroller. So if you take example of few toys, say you might have seen remote controlled cars, where a microcontroller dedicatedly scans for the joystick input, where the wirelessly transmitted to the onboard communication device. So those signals are read, interpreted, and commands are given to the motors of the wheels. So accordingly, it is run, or it may be used for glowing lights or some steering like that. So let us take the example of the home appliances. So here, coming to a taking example as a microwave oven. So we can see that here the heart of the electronics is a microcontroller that is interfaced with a keypad, door switch sensor, that whenever door is closed, the top knob is pressed and the switch is closed and the signal is read by the microcontroller. And also there is a temperature sensor where the temperature of the microwave oven is read so that it can appropriately give input to the magnetron, whether to activate it or switch it off. So there is a fan for circulation of the air inside, and there is a buzzer for giving feedbacks to us or indications, and there is a motor for rotating the turntable, and finally there is a display for displaying the proper relevant information to the user. So here this is a very good mechatronics example where it has multiple kinds of devices all interacting with a single microcontroller device. So here if you see that first the whatever programs written in a microcontroller that keeps on repeatedly executing in an infinite loop. So what it does first, when depending on the state of the system, it will be executing particular task. Suppose if the state of the system is just like now just switched on, and the keypad input is given. For example, for cooking different menu items, we may choose particular numbers. So for that, the number is read by the microcontroller, and it understands that particular number corresponds to particular sequence of operations. And so that operation may be requiring that magnetron switch should be switched on for particular amount of time, and temperature should not exceed say 150 degree. In that case, this microcontroller has to take a decision depending on the other parameters, like now you are giving input and asking it to start without closing the door. So now as soon as you give input, it read the microcontroller and ready to start. Now it goes and check the switch position. If it is not pressed, that means the door is open and it is dangerous to operate the magnetron. So what it does, it will give indication to close the door. And suppose after door is closed, now it will switch on the magnetron, switch on the fan, and start rotating the turntable depending on the type of the program. Then after switching on magnetron for a particular time, the temperature is continuously sensed. So here we can see the temperature device may be analog device, where the analog signal is coming. Again, it has to be sampled to get the digital signal. The digital number is read, checked, and based on that, decision is taken whether to run the magnetron more or switch it off. So these kind of applications are very much interesting, and in robotics also you can see many varieties of application. So coming to another example, like automobile cruise control. So what it does is it takes input from vehicle speed sensor, say maybe some encoders fitted onto the wheel, and steering wheel controls. So where the user can set cruising speed, cruising switch on or switch off, and it also reads the clutch pedal switches and brake pedal So depending on all these inputs, the microcontroller takes ECU. Here it is represented with ECU, ECU for electronic control unit, which is nothing but a microcontroller. So based on all these inputs, it will automatically control the throttle valve based on the parameters like speed and steering wheel control or brake pedal. So suppose if you press a brake when we are cruising, that has to take a decision that this cruise control should be switched off. Like this, many examples may be there. Like another example is a mobile robot, where there may be number of sensors present in the mobile robot, along with the actuators like the motors fitted to the wheel. So here in the front we can see that there is a ultrasonic sensor. So what it does, it sends a sound wave. Then whenever there is an obstacle, so that sound wave is again reflected back, and the receiver reads it, and the time duration which is required to travel by the sound from the source to the object, and then reflecting back to the receiver. So based on this time duration and the speed of sound, the distance between the robot and the obstacle is calculated. So all these calculation will go on this microcontroller. So this microcontroller, depending on the program, it actuates the motors fitted onto the wheels, and takes decision whether to go straight or take turn based on the obstacle information, and also displays the relevant information to the user. And for driving any motors, so we may need a large current. So these microcontrollers may not be able to supply large currents. They are typically in terms of milliampere, but the motors may require this small size motor, or it may take 1 ampere or 2 ampere, in that order. So if you connect directly the motors to the microcontroller, and the motors may pull large current from the microcontroller, and microcontroller may burn out. For that reason, we have to use this kind of motor devices, motor drivers, depending on the type of the motor, where the high current source is supplied to the motor driver separately. So the microcontroller just gives a actuation signal that is read by the motor driver. Then the required current to run the motors are taken from the high current source, and depending on the microcontroller signal, so the switches are on or off to run the motor. So now these are the typical components of the microcontroller. As we have seen in the microprocessor, all the RAM and input-output devices, everything is outside the microcontroller. Here we can see that everything is packed in a single chip. That is the core of the microcontroller is a CPU, and associated with RAM, volatile memory, and non-volatile memory, digital input and output ports, serial communication, which allows us to interact with other devices, and there are also timers. So what these timers does, they simply provide a constant pulses which can be counted and measure time appropriately to take certain actions. So suppose if I want to keep the light on for 1 millisecond and switch it off. So who is going to tell that 1 millisecond is exactly over? For that purpose, these hardware timers are present in the microcontroller, which can be used for generating any signals which requires the time information. So just 1 second. Hello. sorry. Again, to continue with, so we are discussing about the components of the microcontroller. So apart from this, again, analog to digital conversion is there, where it can take some input from sensors, or it can also provide output signals, which can be fed to motors or any other actuators for taking certain action. So this is the general differences between a microprocessor and a microcontroller. So here the basic difference is in the hardware itself, where the peripheral components are not present on the same device, but they are externally attached to the microprocessor. Where in case of microcontroller, all the devices, all the peripherals are present on board, like memory and input-output ports. So here, microprocessor is the heart of the computer system. Microcontroller is the heart of the embedded system. So to see physically that microprocessor, what the CPU, which is present in the processor, and here they may be very much similar, but as if you go by the capacity, microprocessors will have a huge execution capability than the microcontroller, but they are we can say that they are similar, but their architecture may be different. So so as we have seen that other memory and other input-output components are connected externally, but whereas here everything is present on a single chip. So here, as they are provided outside, basically the system becomes the size becomes large, and here it is very compact. And so actually, as this is not compact, sometimes for different tasks it may be very much inefficient, but this is a very efficient architecture where we can control a small process. But here, when you want to take execute large amount of code, or take a decision based on several parameters, then microcontroller may not be feasible. We have to go with the microprocessor. As we have seen that cost is high, and microcontroller costs are very less. So like this, it has several differences depending on application. We will be choosing microprocessor or microcontroller for our industrial or robotic applications. So in some cases, we may be requiring both of them. So each one has got its own their own importance in different applications. So as we have seen, coming to the programming part, that generally we will be using a higher level language to write our codes, and putting that, dumping that into a microcontroller. So in between this higher level language and the machine code, there needs to be a compiler which will change this higher level language to the machine code. So we have seen earlier that in microcontroller there are also present timers and counters. So timer, it is just a specialized type of clock which is used to measure the time interval. So here the source is like for every microcontroller or microprocessor, we talk about the frequency. Like we say that is the processor is of 2.1 gigahertz, like that. So what it indicate is the frequency, where this frequency term is coming. So on the board there is a crystal oscillator which will be oscillating and produces voltage pulses at regular intervals. So the onboard timers takes input from these pulses, and this time duration between on and off time is fixed depending on the oscillating crystal frequency, by just counting the number of, say, if this is 0.1 microsecond. So now by just counting the rising edges, we can simply determine the time. Say from suppose you have counted 3 rising edges, that is 3 into 0.1 microseconds. So the time duration from here to here it is 0.3 microseconds. So when you associate with that time period, then it gives the timer. But when you can also simply count how many times it has encountered the rising edge signal. Depending on that, you can say that it is a counter. But this counter need not be counting the pulses of the crystal which is present on the hardware. It may also be used to count the external source. Suppose, say, a motor is rotating, the motor shaft is rotating at a certain speed. Now you want to sense the speed through a sensor. So commonly we use a encoder. Encoder is again a sensor which can be used to sense the position or speed of the rotating device. Sometimes they are also linear. There may be a rotary encoder or linear encoders. So rotary encoders measures rotational position or velocity. Linear encoders measures the linear displacement or linear velocities. So generally, these construction I will go through in the next slides. So what they does is when the shaft is rotated, when the shaft is rotated, so the encoder gives simply a number of pulses, voltage pulses. So say the encoders are having a particular specification like 600 ppr or 360 ppr, like that. So ppr means pulse per revolution. Suppose when the shaft is rotated, if you receive 300 pulses, 300 pulses. Now that pulse signal need to be fed to microcontroller and that needs to be counted. And if you count based on the number of count, we can say the rotation of the shaft. So if you count 300 pulses, you can say that it has rotated 180 degree. So like that, these timers and counters are very much useful to interact with the physical devices or control some phenomena. And also there are other concepts like interrupts and polling. So so interrupt is a hardware mechanism in which the device notices the CPU that requires its attention. So here, suppose there is a process going on and there is the intervention of the microcontroller is required in that process. Suppose the microcontroller is not checking what is happening in that process, but in turn, whenever it requires computation, that interrupt hardware interrupt mechanism is asking the CPU that I need your attention. In that way, the CPU don't need to check every time that whether it needs attention or not. But in turn, the hardware mechanism itself will tell whenever it is required. So this kind of servicing method is called interrupt. So and the other technique is the polling technique, where polling means that the process which is going on, the microcontroller keeps on checking at a regular interval whether it is connected or not, whether it requires attention or not. Here, the responsibility of attending particular service is lies on the CPU itself, but where the interrupt mechanism, whenever that interrupt raises the notice, then the CPU stops its program wherever it is executing and attend the interrupt, perform those actions, and again come back to the position where it left off. Then from that, it will resume its program. So to give one good example for this interrupt and polling, suppose say when I am in office, somebody says that he will be visiting me today, and I do not know when he will visit. So I need to attend his visit. So if I am following interrupt method, so I don't need to bother when he will come, but whenever he comes, he will call me, so I can attend to him. So another method, like I myself keep on checking whether every 5 minutes I will check whether he has arrived or not, whether he has arrived or not, like that. So this kind of technique is called polling. So when you are doing this polling, what this microcontroller is doing, it is spending a lot of time to check the devices whether they need attention or not. In that way, its resource is consumed and time is being wasted. So whereas in interrupt, we don't need to bother about any attention for others. So we can continue our work. Whenever he comes, he calls, I can stop my work and carry on with his visit. So so that is a very good example for interrupt and polling. So both are equally important. Based on our need, we should wisely choose whether we should implement interrupt in a program or a polling method. So these are the basic differences between interrupt and polling. So in interrupt, the devices notifies the CPU, whereas in polling, the CPU itself keeps on checking whether the particular process needs its attention or not. So interrupt is a hardware mechanism. So the hardware is responsible for notifying the CPU. So there is no program running in it. Whenever, suppose say, whenever some process needs attention, it generates a voltage pulse to a hardware. So hardware mechanism in term, it will invoke the CPU to attend to its service through hardware itself. But whereas this polling method, it is a protocol. So we have to write the particular code for polling. So at what frequency it needs to poll, what needs to poll, whether suppose for example, imagine a keyboard is attached to a computer. Now the computer keeps on polling whether the keyboard is connected or not. So like this, it keeps on checking whenever there is a whenever the keyboard is connected, then it will initialize the device and make it ready for taking the input from the keyboard. So in interrupt, it is serviced by an interrupt handler. So there will be whenever that interrupt arises, there will be a piece of code where a separate function is written for that. Whenever that interrupt happens, what needs to be executed, that is handled by the interrupt handler. But this polling, we have to write entire code in the main program itself, where whenever the polling is done, if something needs attention, that code needs to be executed. So interrupt can take place at any time. CPU don't bother what time it will happen, but whenever it happens, it will serve that particular interrupt through the interrupt service routine. But whereas the CPU in polling method steadily keeps on checking whether particular process is requiring its attention or not. So here, sometimes interrupts can be very much efficient rather than going for polling, because polling consumes lots of resources. Sometimes, say if I am checking whether the person is coming every 5 minutes, so I cannot do my work properly, and whenever if he is not coming, so a lot of times I simply has to return to my work, and every time I will be disturbed to just check whether that person is arriving or not. So this way, in the same way, the polling method also for certain processes, it will be very much inefficient. So depending on the application and the need, we have to wisely choose whether to do interrupt or polling. So here, coming to the practical examples. So this is one basic microcontroller, one of the popular microcontroller board, where it is called Arduino board. So there can be several microcontrollers, but microcontroller needs some peripheral devices. So here, this is the microcontroller. So here it needs power and and a crystal for getting the timing signal. So this is one complete board where the microcontroller is assembled with all the pins and the required power and oscillator along with it. So here, if you want to do any practical task, first you have to choose your microcontroller depending on the application. So even in Arduino also there are Arduino is a commonly used microcontroller units. In Arduino itself, there are several varieties like Arduino Nano, Arduino Uno, Arduino Mega. So basically, in that microcontroller, in each board, microcontrollers are having different specification. So depending on the board, the number of input, output, and the capabilities may vary. So here, basically, this is the power input to the microcontroller, and this is the USB port where you can communicate with the microcontroller, and also it can be used to program the microcontroller, or it can be used to control some other program through microcontroller, and reset switch for resetting the program, and there are some LEDs to indicate the processes. These are TX RX LEDs, that means the transmission line and receiving line for the serial port. And this is on onboard LED, which you can use for indication or for debugging. So apart from that, and there are some voltage pins where suppose you want to run a LED, so you can directly, or you want a 5-volt signal to some other device, you can directly pull from here. If you need 3.3 volt, suppose you want to read a GPS. So some GPS needs 3.3 volt input. So directly that input pin can be connected to this microcontroller board where it can get 3.3 volt. And there are some ground pins and analog pins where it can read some analog signals which are continuous in time domain. So here, whenever we want to read these analog pins, again there will be associated a DAC ADC module on the board, which will convert this analog signal into digital signal, so that this microcontroller can directly read that number. Apart from that, there are some other input-output pins, such as these digital pins. They can be input or output, or it can also generate a PWM signal. PWM signal stands for pulse width modulation. So what is that pulse width modulation? Pulse width modulation is nothing but a signal, or the voltage is controlled through switches to make it on and off. So the time duration where it is on, that is called on time, and when this is off time. And to complete one cycle of this, this is called time period, and the frequency of this change is called frequency of the PWM. So some motors may require this PWM signal. In the last class also, I think we have discussed how we can control the voltage level through PWM signals. So suppose our motor requires a 5-volt input. Suppose the source voltage is 10, then we need 5 volt to control the motor at particular speed. Now we can use 50% duty cycle, where 50% of the time it is on and 50% time it is off. So this kind of signals can be generated with the help of the microcontroller. So if you see that, if you see this Arduino Uno, so there are several digital pins. That means it can control at least 6 to 7 motors simultaneously. So if you take Arduino Nano, that is a smaller version of this, the number of digital input pins or digital input output pins are less. So depending on the application size, first thing is to select the microcontroller board and write the program in that. So here I'm just going through the sample program where in the hardware, so there a LED is connected. So the ground pin is connected to the ground pin, and the positive pin is connected to the pin number 3 of the Arduino board, and through a suitable resistance. So why resistance is required in this case? Because Arduino needs Arduino supplies current in terms of some 100 to 500 milliamps, but the LED may require even lesser current than that. So if you directly connect, large current will flow, and the LED may burn out. So for that, to stop that voltage current surge, the resistor is used. So that is simply a hardware element where we have nothing to do with the program. So just see the syntax of the program. So here I am just giving a brief overview how we can make use of this microcontroller. But if you want to read in and out of this microcontroller, the Arduino, for example, if you take this Arduino board itself, you may get a 600 or 1000 page book where each and every command, each and every procedure is described. So I'm not going into such kind of details, but I am giving a practical orientation how we can use these microcontrollers. So here, if you see the program part of any microcontroller, there are different sections. So in the beginning, we are declaring a few variables. So here in the declaration section, we have defined that we have defined an integer value called LED pin as 3. As we have connected to the pin number 3, we have written number 3 here. So every time when I want to control that pin, we don't need to write number 3. Instead, we can write the name for it. Because if you have several devices connected to these pins, every time you may not remember whether I have to use 8th pin or 9th pin. Instead, you can name those, and very easily you can remember that names and write the program. Suppose LED is connected to pin number 3, and suppose a motor, a PWM signal is connected to pin number 4. So now you can write a motor pin. This variable, there are certain rules which how to name the variable, whether special symbols are allowed or not, capital or small, whether it is case sensitive or not. That details you can get from any C language book or Arduino controller book. So like this, you can name certain variables, and you can use them in the main program. So in the next section, it is the setup. So just to make sure whether, so everybody is able to follow what I am going through.
Yes, sir.
Okay. So this next section is a setup. So where we are initializing certain things, or getting ready for the execution of the main program. So here we are initializing the input-output pins also. So if you see here, pin mode, this is a keyword. So to see the list of keywords, you have to go through particular microcontroller book to see what this corresponds to, or whether this keyword you have to use or some other keyword. So here, this pin mode is a keyword which is to tell that whether the pin is used as an output or an input. Suppose if you are reading a sensor, then we have to make that pin as input. That means we are collecting the signal as input to the microcontroller. So here we are giving the signal to the LED. So we are telling that it is an output pin, where the microcontroller will send a certain voltage as output. So now the setup section is over. Now once the setup section is over, the program flow will continue to this main program. So in Arduino, it is written, every program is written with this void loop function, where this loop executes continuously. So the program flow will be like this. So sequentially, all these are executed. So assuming that there are no other functions or other interrupts, as the case in LED program. So it comes in this main program, and it keeps on executing this function loop. This is the main infinite number of times. So first what it does, executes the instruction one by one. So now it is writing digital write, because it is a digital pin. We are using the keyword digital write LED pin. So LED pin, it refers to 3. That means we are telling that you write in pin number 3 a high signal. High signal means here the voltage range of these microcontroller pins is from 0 to 5 volt. So generally, when you ask to make it low, it puts 0 volt. Then if we ask to make it high, it makes the pin 5 volt. So now we are asking it to make the pin high. That means as soon as this instruction is executed, this pin becomes 5 volt. Here 5 volt is present at that time. Then the current flows into the LED and this glows. So now until unless this is interrupted or this is disturbed, this pin continues to hold that particular high value. And coming to the next line, we are asking to wait for certain time. This delay is one command where the program execution control is held up here. So this value is in millisecond. So delay of 1000 means it will wait for a second. That means it made the pin high and it waits for 1 second. Then only after waiting for 1 second, then only it will execute the next command. That is again making the same pin low. That means again it makes 0 volt here. So when it makes 0 volt here, again the LED is turned off. So again wait for 1 second, then again make it high, wait for 1 second, make it low, wait for 1 second. So this cycle here, it keeps on repeating. So here the program, whatever you write in a microcontroller, that is written in the loop. That is a kind of infinite loop. So generally in normal program, we never write any infinite loop programs. So we used to write some break conditions where it has to come out of the function. But here, all the microcontrollers will have an infinite loop function where it will keep on executing the same function repeatedly for countless number of times till the power is off. So there is also a reset button we have seen. So what this does is when you press this reset button, wherever it is executing, it will stop and it will again start from the beginning. So again, and these are all executed once, and it comes to the loop function and keeps on executing. And whenever it is again powered off and powered on, again it will start from the beginning. It is powering it off and on is equivalent to a reset button press. So this there are a few more practical examples. I'm not going through this block diagram. So earlier we were discussing that encoders are used, optical encoders are used for sensing the motor speed for any revolving shaft. So here this picture depicts the basic construction of the encoder. So schematically, there is a disk where it has several tracks marked on it. So the tracks are coded like the black portion represents opaque, and the white portion, it is clear. That means whenever we put light on one side, it passes through the clear portion and it can come outside. So here when the disk is coded, on both the sides. One side there are infrared emitters, which are kind of LEDs, and there are photo transistors, which are the which can sense light. Okay, which can sense the light. So what happens? Suppose this disk is coated with opaque and transparent region. Whenever the light try to encounters this opaque region, the light cannot pass through. But whenever the shaft is rotated, and at the same time, when the light encounters this clear path, it is transmitted to the other side and received by the phototransistor, and it will raise a voltage pulse, so which can be read with help of microcontroller. So now when the shaft is rotated, now we can see the if you see the output of these phototransistors, so we will get a series of pulses depending on the speed of rotation. So by just simply counting the number of pulses, we can calculate the rotation of the disk. Suppose there are such 300 tracks on this. So if you receive 300 pulses, that means it has rotated 360-degree. But if you receive only one pulse, that is 360 by 300, that is a total amount of displacement done by the shaft. So as we are using optical based thing, we are calling it as a digital optical encoder, and the output of this signal is also coming like a pulse, so which can which can corresponds to 0 or 1. So we are not seeing how much voltage it is, we are only seeing whether it is high or low. So when it is low, it is 1, when it is high, it is represented with 1. So due to this reason, we are calling it as a digital optical encoder. So there are different types of these encoders, and there are also different sensors for measuring the motor rotation, like resolvers. But I'm just giving a just brief introduction for this optical encoder only. So these rotary encoders divided based on this signal output and sensing technology. So signal output can be incremental or absolute. Incremental means whenever the device is powered on, that position is marked as 0 degrees, and from then onwards, whatever number of pulses it receives, it simply counts the pulses and says that the relative displacement from the beginning, it is 30-degree or 60-degree or whatever. But in case of absolute encoders, these track patterns are coded based on the binary or gray code. So each particular position, so here in this case, you see the track is marked with opaque and transparent at a regular interval. So whether this opaque region or this transparent region, it has no difference, it is same. So wherever it starts, it makes thinks that it is 0 degree in case of incremental. In case of absolute, the track patterns are different. So in this case, you see, if you draw a line at any place, so the opaque and transparent region, and here it is different, and here it is different. So this track pattern is particularly arranged based on the binary code. So each position corresponds to a particular position. So even when the power is switched on and switched off, so the absolute position can be sensed. So depending on these, we can call them as incremental or absolute. So there are different other sensing technology based on magnetic field or optical or laser. So in case of resolver, laser light source is used by sensing the phase difference between the reflected signal. We can sense how much displacement has been done by the motor shaft. So, and the other practical example is related to our developments in our robotics department. Here we can see one controller made by us, which is used to control the thrusters. So here again the microcontroller portion you can see where the microcontroller is embedded onto this board with several peripheral devices where there are some communication ports like RS-232 USB port and the power input, and there is a fuse for protection, and there are some DC-DC converters and voltage regulators for providing appropriate voltage to the microcontroller as well as the to the output ports. So here basically what I am trying to say is that these practical applications will be like this, where suppose if I want to control the thruster speed, I will communicate to this board through RS-232 or USB port. I will send a command through this. Now the command is read by the microcontroller. Now microcontroller, after reading and interpreting the command, it will generate a series of PWM signals from these digital pins. Those digital PWMs are conditioned and given output to the ports. Suppose why this PWM is altered to the output ports is because say microcontroller can only give 5 volt PWM. That means it can be on and off at a range of 0 to 5 volt. But certain devices needs a 12 volt PWM where the on voltage should be 12 volt. So here what we does is we will simply take this PWM signal and decouple them through optocouplers and provide we are providing external voltage where suppose if we are giving 24 volt input through these voltage regulators, 12 volt can be produced or this kind of DC-DC converter. So by this microcontroller 5 volt is just a kind of signal where it is read when this 5 volt is on. So we will turn this 12 volt switch on. So 12 volt will flow into the output. So like this, we can generate a lot of PWMs to control 6 thrusters simultaneously with the help of this. So here you can see the another practical example where we are using one single board computer as well as a microcontroller, dedicated microcontroller in ROV application. ROV stands for is a remotely operated vehicles, where the user can interact with this vehicle through a joystick and an umbilical cable is connected. These are two different ROV systems. So these are two different vehicles. The user commands are passed through this umbilical cable. Generally, they are very much. This can provide very long range communication up to 500 meter or more than that. So this communication is happening with RS-485, and the user is using some joystick to provide commands to the vehicle, and those commands are going to so here you can see the architecture. So those commands are going to this SBC. There is a single board computer, and those commands are interpreted, and based on that interpreted commands, see here it has to, this SBC has to read several other sensors and do execute a large program. So that's why we are using one SBC here. So once the commands are interpreted, the six thrusters are these are the 6 thrusters, underwater thrusters that needs PWM input. So continuous PWM input that is generated by this microcontroller. So now once the all the commands are interpreted here, it sends out the communication to Arduino microcontroller. This microcontroller generates PWMs, corresponding PWMs, and it will actuate these thrusters. So here you can see a small video how this is working. So the user is interacting with the help of this joystick. Those signals are passed through the umbilical cable, and the SBC is interpreting that and communicating to microcontroller. microcontroller is taking action by generating PWMs to actuate the thrusters. So this is all about brief introduction to microcontrollers and data acquisition portion. If you have any questions, I'm pleased to attend to those. Anybody is having any question?
No, sir.
No, sir. Do we
So,
use Python programming?
Python is not used for microcontrollers. So mostly C language is used, and see, it is all depending on the availability of that assembler. So if anybody can generate assembler for Python language, you can also use Python language for microcontroller. But mostly this Python is used for programming single board computers, where like robot operating system, that kind of applications. So they are very much useful in programming SBCs rather than microcontroller. So if anybody can make assembler for Python, definitely Python also can be used. Or for that matter of fact, any language can be used. Any more questions?
No, sir.
Okay, I hope this would have helped you to have the practical orientation towards these microcontrollers. And the next class would be on again Sunday, and Dr. Srinivasan will attend to that class. Will take that class. So with it, I am closing this call. Is that okay?
Okay, sir. Thank you so much.
Okay. Thank you very much.
Yes, sir. Thank you, sir.